Understanding characteristic impedance of transmission lines. Here we have a line with the voltage source across it, V0. The line goes on and on and on. We know from previous work that V equals V naught plus times e to the minus gamma z represents a wave going in the direction of increasing z to my right. The current is I naught e to the minus gamma z, and I naught is the voltage divided by the characteristic impedance Z naught. We're trying to get some intuition around Z naught here. Previously, we saw that for a lossless line, Z naught corresponds to LV, where V is the velocity of the wave in the lossless line, written here, and you can see that there's a slight cancellation, and there's our result for Z naught. And in this case, the line has a constant inductance and capacitance per unit length. For the case we're studying, it's a lossless line here, so gamma, which is alpha plus j beta, becomes, for the case of alpha equals 0, gamma being j beta. So we're going to substitute in for the ratio of V over I, and when we do that, that has units of impedance. So the units of impedance are ohms, and if you're looking at impedance per unit length, it would be ohms per meter, but in this case, it's definitely ohms. You can see this because this is henries per meter divided by farads per meter. The per meter cancels out, so the right units, of course, are ohms, not ohms per meter. We look at this ratio and we notice that the exponential factors cancel out. So what do we get? Sam, where are you, Sam?
Hey, Matt.
Oh, Cookie Monster!
Nom, 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 nom.
So Sam, between cookie bites, this ratio then becomes Z naught. What's special about this result?
So I see that you've canceled out the e to the j beta z term, negative j beta z.
Yeah.
So I guess this means there's no more dependence on where in the line you are. So anywhere on the line, you get Z naught. Is that right?
That's absolutely right, and we're going to see it following this set of equations, more how to explain the intuition around Z naught and Z naught being constant as we go along the line. And what that actually means. What do you say, Cookie Monster?
Nom, 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 nom.
Well, Sam, let's continue our intuition and understanding here. So I'm going to ask you a question. Let's look at some point along the line.
Okay.
And we'll look at Z is equal to negative L, some distance, negative distance. So what's the characteristic impedance at this point?
You like from this point looking towards the end of the
Yeah,
line?
just
Well, Z naught.
Z naught. How about if we look at Z is equal to 0? What's
So if
the
you look from
characteristic?
here to infinity,
Right.
Z naught?
Z naught. And how about at infinity? What's Z naught at infinity?
Z naught.
Z naught. So this is to underscore that no matter where you are along the line, it's always, and this is a lossless line, same properties along the line, it's always Z naught. Even Z naught is equal to Z naught even at infinity. So I don't want to keep writing down infinite lines with dot, dot, dot. So how can I model this part of the line from here to infinity?
We can just put in a load there and say the load is Z naught.
Yeah, because the load looking in is always Z naught. So we can erase, thank you, erase everything here and replace all that line by a load, as Sam just said, equal to Z naught. So we can draw in our little load here, and that load is ZL for load, and that's equal to Z naught. So there we go. That's
Looks good.
kind of cool. So now let's try to get more understanding around what this impedance is, because there's some intuition still missing. So we'll start with the load equal to Z naught. Let's change places here. You can think of Z naught as like the electrical stiffness of the line. So I'm going to pretend that I'm a wave and I'm going to be pushing Sam. So if the wave is coming and it's always seeing Z naught, this is what's going to happen in terms of pushing. I'm pushing, I'm pushing, I'm pushing at a constant speed all the way down the line. And it doesn't matter because the impedance that I see in pushing is always going to be Z naught. Now, what's going to happen is if Sam is sitting, say, at this point in the line, and I'm a wave coming, now Sam is going to be a little stiffer. So we're going to have a second picture now. I won't draw the whole thing. In the second picture, ZL is greater than Z naught. So I'm going to be feeling Z naught all the time.
So I'm stiffer than the line itself.
So he's stiffer, he's bigger than Z naught, and I'm a wave, I'm pushing against Z naught, I'm pushing against Z naught, I'm pushing it, but Sam isn't moving, so it's stiffer. And notice what happened when I pushed, I bounced back. So the point about this case is when the wave travels down a line that has characteristic impedance Z naught and hits a load, when Z load is greater than Z naught, we get
Some reflection.
reflection.
So me as the load absorb some of the incoming energy, but some still get reflected.
Right, so we have forward, reflected, and transmitted into the load. So what will happen if we put the load, Z load goes to infinity? Let's make the load that. So that's what's that called, Sam, before we do
Open circuit.
open circuit. So here comes the voltage wave. It's coming, it's pushing, and reflected back. So now it's open circuit. Sam, what is the load impedance doing to the reflected wave when ZL is infinity and we have open circuit?
You mean due to the incoming wave, everything gets reflected because the open circuit does not consume any of the incoming power. Is that right?
That's right. The open circuit does not allow any power to be transmitted, so all is reflected. Good work.